Okay, we'll wait for one more minute for everyone to be back from the breakout session. And then we will start with a very exciting session where we'll have Yiju give a keynote talk on the use of graph neural networks for graph search. So it's really a pleasure to introduce someone as prolific as Yiju, talking about such an exciting topic for graph search, which is a graph data management problem, and looking at this problem through a machine learning lens, which is using graph neural networks to solve such a interesting optimization problem. So Yiju is an assistant professor at Department of Computer Science in UCLA. And prior to that, she was an assistant professor of the College of Computer and Information Sciences in the Northeastern University. She received her PhD from University of Illinois at Urbana-Champaign in 2012. And she is mainly interested in the areas of mining on graphs and networks. She has done a lot of research in heterogeneous information networks. She's one of the pioneers in that field, and now she is trying to just do the same in the field of graph neural networks. So without much further ado, I would like to welcome Yiju to give this exciting keynote talk, and the stage is all yours.
Thank you, Ankir. Thank you for the invitation and nice introduction. So I'm going to share my screen now. Can everyone see my screen? Okay, thank you. Going to have the presentation mode. Going to have the pointer. Going to minimize this. Okay, so yeah, today I'm going to introduce how we can use graph neural networks, like as Ankir introduced, right, from machine learning perspective to solve a very standard classical graph database management problem, which is graph search. So as we are in this workshop, right, so then I think everyone already know that, okay, graph is very important, right? Graph are very important because they kind of are ubiquitous in different domains, in different applications, from social network to like proteins, chemical compounds, to things like less kind of standard in terms of graph, for example, the kind of code or software and even hardware. Okay, so all of them can be represented as graphs. So on top of these graphs, right, so then people try to understand what's going on, and they want to kind of study different kind of functionalities on top of those graphs. So then for us, we think that for all those different tasks, then they can mainly be divided into two categories. One is called node level functions, and the other is called graph level. Okay, so for the node level functions, then probably you can imagine like in a social network, right? So the system wants to recommend the most similar users to yourself, right? So then it's kind of node level similarity search. And similarly, you can do this node level classification. For example, try to understand a person's political ideology, or do community detection, try to identify some community which also comprise of people. And also, like, for example, the ranking, right? So we want to identify which node is more important. In contrast, graph level functionalities are the basic units actually are graphs, right? So in terms of similarity search, then we are interested to find the most similar graphs to the query graph, right? Which is different from the node level similarity search. And also we're interested in many other things, for example, graph matching, as we discussed in the previous talk, right? And also the graph level classification, for example, giving a chemical compound, can we know whether it's toxic or not? Okay, also we can do graph level clustering and many things like that. So for today's talk, we're going to focus on the highlighted bullet here, which is like how we can do similarity search at the graph level, right? So it's like, as I said in the beginning, it's a very classical graph database management problem, right? So before that, I will try to introduce a little bit about the current situation, how people propose graph neural networks to solve this graph-related problems. Okay, so recently, due to the development of deep neural network approaches, people realized that actually we can also develop neural networks for graphs, right? So then kind of similar to the node level and graph level functionalities, right? So we can also try to categorize all those graph neural network approaches into node level and graph level. So up to now, still, there are more node level graph neural network approaches than the graph level ones, okay? And but anyway, for all those approaches, the basic idea is that how we can represent the node in a graph in a like a low dimensional vector, and how we can represent a graph in a low dimensional vector. Okay, so with the vector representation of those graphs, then we can kind of reconsider our kind of standard problems in a completely new way. Okay. So here I also want to introduce one of the most popular graph neural network methodology, which is called a graph convolutional network. Okay, so for graph convolutional network, by just looking at the name, then probably you can imagine that it's kind of inspired from the standard convolutional neural network, right? So it tries to extend the CNN from the regular kind of image, those domain to irregular, like the general graph domain. Okay, so for CNN, the general idea is that then for each pixel, right? So we need to leverage its neighbor's information, okay? So which is called a convolution operator. And then we can do some kind of transformation and do some fooling, right? So then we can capture so the invariance of the kind of the property of that image data, right? So in graphs, right? So the idea is quite similar. Okay, so here if you look at a toy graph here, right? So then definitely we have like 4 nodes and a couple of links between them. So then in order to get a good representation for a node, let's say node 1, right? So it also leverages its neighbor's information, okay? But different from the image domain, right? So then your neighbors is kind of fixed. For a pixel, you have your up neighbor, down neighbor, left and right, and maybe diagonal places, those neighbors, right? But for a graph, there's no such regular structure. So for each node, you really need to just try to identify who your neighbors according to this agency matrix, right? So for example, for the node 1, then we know that, okay, it has 2 neighbors, 2 and 3. And also, you also want to include yourself. So that's why the extended neighbors, it's like 3 nodes. And then for the node 1, then we're going to include all the 3 nodes information, okay, do some sort of average. And after that, we're going to map that vector into a new space using this linear operator. Okay, after that, we're going to do a nonlinear activation to kind of make the function much more powerful by introducing this nonlinearity, right? So the whole thing is called one layer, okay? So after this one layer, then you can imagine that now every node that can be represented as a new vector, okay? And then you can repeat this, right? So for the second layer, similarly, okay? So then for each node, you can aggregate all your neighbors' information, including yourself, and then do another transformation, okay? And then another nonlinear activation. So after the layer 2, then you can have a new representation to every node, right? So if you are interested in those node level downstream tasks, then you can directly leverage those node level representation and feed them into, for example, node classification or link prediction tasks, right? So then according to the guidance, you can do back propagation to update the parameters, right? So here the parameters, you can imagine that it's just a W1 and W2, which involves in this nonlinear transformation, right? And if we are interested in this graph level operation or graph level downstream tasks, for example, this graph level semi-research, then we have to kind of do some sort of fooling, right? So for all those nodes, we want to aggregate them together to get a graph level representation. And how we can do that, right? Of course, a very simple way is that we just do an average of all the embeddings of those nodes, but definitely it's not a good way, right? So then later we're going to talk about that, how we can do aggregation in a smarter way. So that's the introduction to the graph convolutional network, which is like one of the most popular GNNs we're talking about. Now let's move on to the task that we are interested in this particular talk, right? So we're interested in this graph search problem. So just a simple recap for the so-called graph search problem is like given a graph database. So you can imagine that it's a database of drugs. It could be a database of all the software snippets, right? Considering that each software snippet has already been converted into graphs. It could be a protein database, right? So every data point here is represented as a graph. Okay, now suppose you have a query, right? Suppose you want to kind of try to search the most similar drugs to a given kind of chemical compound, right? So in this case, you have a query, which is also represented as a graph. And then the goal is that how we can find the most similar drugs in this database. Okay, so that's the general idea. Okay, and of course, for this problem, it's a classical graph database management problem, right? So there are tons of different approaches to try to solve this problem. And in general, the framework is called pruning and verification. So in the pruning stage, people try to build this graph index, okay? So using all kinds of heuristics, try to design this very nice index such that by using this index, we can quickly identify the most promising graph candidates. And after that, then we can apply this more expensive exact computation between the query and one of those candidates. Then we can have this exact number, right? So then based on that, then we can do a sorting, and then we can return the most similar ones. Okay. So for those methods, right? So definitely involves lots of like heuristics, lots of feature engineering, right? And lots of tricks in implementation. So that's why first, it's very difficult to design. And second, it's very difficult to implement, okay? So it turns out that when we try to kind of compare with those baselines, we find that many of those like code, okay, it's very difficult to run, okay? So then we wanted to solve this problem in a more automatic way, right? So can we kind of automatically get all those features, right? So it's like we just turn it into kind of learning problem. Okay, we just learn something. Okay, in the end, the design is not that difficult. Okay, also the implementation is not that difficult, right? So in order to solve this problem, then we try to sit down and carefully think about what will be the fundamental operators we need if we really want to make this procedure more automatic, right? So then we come up with two operators. Okay, the first operator is called the graph similarity computation operator. So the general idea is that given two graphs, okay, we want to directly compute its similarity. It's approximate, of course, but it's going to be much, much faster than the exact solver. So later we're going to discuss why this graph similarity computation itself is a problem, okay? The second thing that even we can compute the similarity given a pair of graphs in a very efficient way. But given a query, right, we definitely don't want to go to every possible graph in the database to compute the pairwise similarity. That's why we need a second operator. The second operator says that we're going to represent a graph in a very nice way, okay? Then with that representation, we can easily use some kind of vector-based index methodology, right? So then we can use vector-based similarity computation to quickly identify the most promising candidates. Then we can go back to the first operator to quickly compute the similarity between the two. So that's the general idea. So then in order to illustrate this in a more vivid way, we just provided this illustration here, okay? So for the first operator, it's like given two graphs, right? After this neural network-based operator, so we can directly output some number which indicates their similarity or distance, okay? The second operator says that given a graph, after this graph neural network, then we're going to map it into a low-dimensional vector. Okay, so that is going to be a good representation of this graph. Then how we can say whether this representation is good or not, we're also going to discuss later. Okay. So now let's come to the first operator, which is the graph similarity computation operator, right? So let's start with a very concrete distance between those graphs, right? So which is also very popularly used, the graph edit distance. So here I want to mention that I don't want to advocate some distance over others. Okay, so here what we wanted to say that this distance could be very general. So later, if you're not happy with graph edit distance, if you want to use maximum common subgraph or some other distance or similarity matrix, you can easily replace that. So here we just want to use this graph edit distance as an example to illustrate our methodology. Okay. So then what is this graph edit distance, right? So essentially GED, graph edit distance, is a distance try to compute the distance between two graphs according to how many edits we need to have. For example, for the first graph, we needed to kind of cut an edge, add another edge, and change the label of the node. So then we can finally come to the last graph, right? So then we need 3 edits, okay? And it's minimal edits we need. So then that's going to be the distance between the two graphs, okay? So this problem is NP-hard problem, okay? So the 2 years ago when we started to study this problem, okay, according to the literature then, right? So then in order to compute the exact GED, right? So then it turns out that we cannot finish the running within a reasonable time between graphs with more than 16 nodes. Okay, 16, it's just a small number, but for the exact solver, yeah, we just cannot compute that because of the NP-hard nature, right? So then what would be the traditional solution to address this problem? Of course, we have this exact solution, which is exponential time complexity solution. We also have some other approximate solutions. So they are mainly from the combinatorial optimization, this line, okay? So then it's based on lots of human heuristics, okay? And it's based on the search, okay? So again, it's difficult to design and implement, okay? And if you look at the time complexity here, actually it's also, although like for some of them it's already polynomial, but it's still in practice, right? So it takes a long time, okay? So then our goal is that, can we just make things simpler, right? So can we just try to design neural network such that given a pair of graphs, then we can have this distance, right? So to formalize it, right? So we want to learn an operator called phi, which takes 2 graphs as input, okay? And we wish that after this computation using this graph neural network, then it's approximate the distance we want, the GD distance we want. So here I want to say that in practice, we don't handle GD directly in this paper. We're just using a like 1-1 mapping function to convert GED distance into a similarity, which between 0 and 1, so which can make our learning procedure more robust. Okay, and this phi, this operator definitely needs to have some good properties. The first and most important thing is like we need to make it permutation invariant. So in other words, if the graph is represented in different way by changing the ID or node ID order, right? So then we know that we are going to have a different agency matrix, but we wish that our operator phi is not going to be affected by that. And the second, it has to be inductive, which means that once we have some unseen graphs, okay, so then this unseen graph can also be fit into this operator phi, okay, so we still can compute the distance between this unseen graph and some other unseen graph, or this unseen graph with some other seen graph, okay. So the third property is called learnable, okay. Learnable means that if today we're interested in GED, but tomorrow we're interested in MCS, right? So then we can safely replace the loss function part, okay. We don't have to change the architecture. We just need to use a new similarity matrix to retrain the neural network, and we're done. Okay, so we need to make it learnable. So here it's just a recap of this graph isomorphism problem to indicate that the same graph can have different representations, and we need to always keep this in mind that we don't wish that our operator will be affected by this fact. Okay, so then what would be the solution? So then we propose our first solution, which is called SimGN. Okay, so it's done by my student Yunshen Bai. So he's right now a third-year PhD student, but he has already done lots of work along this line. So for today's talk, majority of the work is the results are mainly produced by Yunshen. Okay, so for this first solution, which is called SEMGN, okay, so we think about two different strategies to solve this problem. The first strategy that can we learn a graph level embedding? Okay, so now each graph is going to be represented by embedding vector, such that this embedding vector can directly preserve the proximity that we want. Okay, so that's a strategy one. But there are some drawbacks of strategy one. The general idea is that if we just use one vector to represent one graph, definitely it's too coarse, right? So can we make this comparison in much more detailed level? So that's why we also want to have this strategy two. Okay, so for the strategy two, the idea is that in the end, suppose we have run some graph neural network, right? So then every node will have a good representation in terms of vectors, right? And then every graph is going to be represented by a set of nodes, right? So in other words, it's going to be represented by a set of vectors. Can we directly compare those two sets of vectors, and then we can compute the similarity between two graphs, right? So then back to strategy one, okay? So then what we are doing is like, okay, we're going to have this graph level embedding. That's what we want, right? So then the challenge is that how we can aggregate all the nodes in this graph and then come to one vector that can represent this graph, right? So definitely we cannot use average because we average assume every node is equally important to each other. This is not the case, right? So that's why we try to put attention to different nodes. So in the end, this graph level representation is a weighted combination of all those nodes, okay? And this attention definitely has to be learnable, okay? So we're going to also put learnable weights on this attention mechanism. And second, once we have this graph level embedding vector, right? So for graph A, we have a vector, graph B, we have a vector. Then we're going to have more sophisticated computation to use these two vectors to compute the similarity between two graphs, okay? So then in our case, we use this so-called neural tensor network. So this is a kind of also standard approach, which means that given two vectors, we're going to use this neural tensor network to capture different aspects of this similarity. So if it's like k dimension, then the output of the neural tensor network is going to be a k-dimensional vector, okay? And finally, it has to be guided by the proximity that we want in our GED case, right? So then it has to be this GED transferred similarity, okay? So that's strategy one, okay? So due to time, I'm not going to disclose too much details, the formulas and things like that. But here, I just want to deliver the high level idea, okay? And then now let's come to the strategy two, okay? So for strategy two, the idea is that can we directly kind of compare two sets of node level representations, right? So here, the challenge is that since we do not have a good order of those nodes, okay, then the problem is that if we switch the orders or we kind of flip the orders of those nodes, then we'll have different representations. And that will give us trouble when we try to compare two sets, right? Because once we have two graphs and we know that, okay, each graph is a set of vectors, right? So then we can naturally compute the node-node similarity. So it's like given one node from graph A and one node from graph B, then we can directly use the node level representation to compute the similarity between those two nodes. So that gives us this so-called similarity matrix. So this similarity matrix M by N, M is the total size of nodes in graph A, and N is the total size of nodes in graph B, right? But here, the trouble is that if we kind of shuffle the order, then the similarity matrix is going to be completely different. Okay, so that's why we cannot directly use this matrix as input to the following graph neural networks. So then what should we do? So we just try to think about what will be the invariant things in this similarity matrix. Okay, so then it turns out that we can use histogram to represent the overall distribution of the values for those entries in this similarity matrix, right? It's n by n matrix. For every entry, it's a node similarity number, right? So we can use histogram to capture the distribution of all those numbers, right? And this definitely is not going to be affected by the different orders or different representations of graph, right? So that's the general idea. Okay, so that's why we have the final architecture. So this architecture says that, okay, for two graphs, we just first feed in them into GCN or other graph neural network. So we can get the representation for each node. Okay, once we got the representation for each node, then we're going to have two strategies, right? So for the first strategy, we're going to use attention mechanism to get this graph level representation. Once we have this graph level representation, then we go to the strategy one, which is the neural tensor network. So we can have this k-dimension output to capture the different similarity at different aspects. So that's going to be the blue vector here. Following the second strategy, right? So once we have the node level representation for each graph, then we're going to come here to form the similarity matrix. And in order to still make everything permutation invariant, we just capture the histogram of that similarity matrix. And then we treat that histogram as the second vector, right? So we concatenate the blue vector and orange vector together and we fit it into MLP, then that will give us a final predicted similarity score. We're going to compare that predicted similarity score with some ground truth. In our case, it's GED, transform similarity score. And then we're going to backpropagate the guidance, right? So then we're going to update the parameters here. Okay, so now let's check whether this SimGN satisfies those three properties we want. Permutation invariant, yes, because for GCN, right? So it actually does really rely on the representation of the graphs. And in the end, when we come to the strategy one, right? So it's kind of aggregation of all those node level embeddings, right? Also the order of those nodes do not matter, okay? And for strategy two, right? So we have the careful designed kind of histogram, right? So that's why it does matter either, right? So for permutation invariant, yes, it does have this property. And what is inductive? Yes, because once we have a new graph, right? So it doesn't matter. We just still we can input that from the whole architecture, right? So we can just do the strategy one and strategy two. Doesn't matter. So we can do it for the unseen graphs. And whether it's learnable, yes, because if we replace the training part, right? So if we replace the ground truth, then everything can be retrained without changing the architecture. Okay, so that's why this is a very very flexible operator and very good because it has satisfied all those three properties. So then we compare our SimGN with some other baselines on top of those different data sets cover from different areas. For example, for this one is like chemical compounds, Linux is like program dependency graphs, IMDb is like social network derived graphs, okay? And for the matrix, we want to measure whether it's effective and efficient, okay? For the baselines, there are two lines of baselines. One is the traditional kind of GED computation methods based on the combinatorial research. And for the second type of approach, it's like graph neural networks, but they did not have this careful design as we claimed, okay? And for the training preparation, I want to emphasize a little bit because it's different from the traditional training process, because right now, what we want to do is compute the similarity for a pair of graphs. So that's why if we look at the training, okay, so then we're going to partition our graphs into training, validation, and test, okay? But the training points actually is defined over those pairs, okay? So that's why here each row and each column corresponding to a graph in the database, right? So for this area, the training area, is like we're going to utilize the graphs in the training data set to prepare the ground truth, right? And this blue region is like one graph is from the, so it's like, for this validation, it's like prepared from the graphs from the validation graph data set. But again, remember that we need to compute the pairwise similarity, okay? And for the test stage, we'll say that, okay, for this region, right? So we actually try to predict the similarity between the unseen graphs and some other graphs that have seen the training and validation. And for this part, you can imagine that actually for two of those graphs, right? So neither of them have appeared before. So it's completely unseen for both of the graphs, but we still can do a good job for the prediction. So for the effectiveness part, okay, compared to both lines of approaches, neural network-based approach and the traditional combinatorial research-based approaches, right? So we'll say that our performance is super, okay? It is much, much better than the traditional combinatorial-based approaches. And efficiency-wise, it's super fast. Okay, so actually we can say that if we just use strategy 1, then it's proportional to the number of edges in the graph. And if we use strategy 2, right, so then it's kind of proportional to the number of nodes square, okay? So in other words, for our approach, compared to the traditional methodologies, it's faster and it's more accurate, right? So there's no trade-off. So it's something also surprised to us, okay? So we expect that it's going to be faster, but we didn't expect that it's also going to be more effective, but that's the observation we have, okay? And here I just provided some case studies, right? So based on the ACE data set, okay, you can imagine it's like chemical compounds data set. So for the top row, okay, it's just the exact result returned by the exact solver, okay? And for the second row, it's returned by our approach. Actually, it's quite similar, right? Also for the Linux data set, it also has a similar phenomena. And another very interesting question that for the strategy 1, right? So remember that we wanted to put a different attention to different nodes such that we can do a weighted combination of different node level representations to get this graph level representation. What kind of nodes we have attended, right? So here we can say that the nodes we have attended, for example, this atom, right? It's also kind of consistent with our human intuition, okay? So which also provided some interpretability, okay? So that's SimGN, right? So then, of course, there are like limitations of SimGN, right? So for example, for the strategy 2, actually it's going to be super important. But for SimGN, actually we oversimplify this process by just to kind of have some simple statistics, which is represented by this histogram to capture that information to make everything permutation invariant, okay? And also I hide something here. Because of the histogram, it's not a differentiable operator, right? So that's why when we do the backpropagation, we can only do the backpropagation using strategy 1, okay? We can not really use strategy 2 to guide the parameter learning part for our graph neural network. So that's why we propose something else, okay, which is called a graph sim to solve this problem. So for graph sim, we wanted to just utilize the strategy 2, but in a much more sophisticated way, okay? So why, again, so here I want to emphasize why we still believe that when we measure the similarity between two graphs, we really should look at the two sets of the embedding vectors. So here, just a motivating example, okay? So for two graphs that are exactly identical to each other, right? Suppose we have a good order of those nodes. Okay, so that suppose that assumption is very important, okay? Suppose we have a good order of those nodes, then if we plot this similarity matrix, right? So we can see a very good diagonal block pattern, right? Because essentially it's like a node is going to be similar to its corresponding part in the other graph, which is isomorphic to this graph. So that's why we can see this very clear block pattern. So if we change one of this graph slightly, right? So we still can see that kind of block pattern, but it's less severe, right? So if we change this second graph into a graph is nothing in common with this graph A, then we can see that this kind of pattern is gone, right? So that's why we have a strong belief that this similarity matrix actually captures the information to tell people how we can align these two graphs together, okay? And here we just use kind of block pattern to describe this kind of pattern in a high level. But actually we should rely on the graph neural network to capture the more subtle features that our human eyes cannot identify and our human brain cannot do the reasoning, right? So that's why we think that once we have the similarity matrix, we can just treat it as an image, right? So then we try to fit this image into some like convolutional neural network, and we treat it as kind of image regression problem. For each image, we want to use this convolutional neural network to directly predict the similarity. Of course, before that, there's lots of subtle things we need to handle. For example, the permutation invariant thing, right? So due to the time, I'm not going to the detail, but here I just want to say that we kind of have some very naive solution to fix the order of the graphs. So then partially solve this permutation invariant problem. So then given each pair of graphs, then we can have this similarity matrix. And the second high level message I want to say that we do not just provide one image for a pair of graphs. We're going to provide a couple of images indicating different level of similarities for the same pair of graphs. And then we're going to feed those, like in this case, we're going to feed those 3 images into CNN, okay? And then it's like channels of different channels of the same image, right? So we're going to have different images for the same pair of graph. And then we're going to feed that into CNN, and we can make whole thing kind of differentiable. So then it's going to be end-to-end framework. And in this particular task, we actually tested over not only GED, but also this maximum common subgraph, try to show that indeed we can handle different graph similarity measure, okay? So in this case, okay, so if we look at the results here, our graph sim, okay, is much better than SimGN, which is our initial attempt to solve this problem, and also better than some other graph neural network-based approaches. And if you look at the combinatorial search-based algorithm, right? So compared to the neural network-based one, it actually is much worse, okay? And for the MCS, the conclusion is similar, okay? So which means that indeed our architecture is quite flexible, okay? So once you replace this GED with MCS or other metric, you can still do a good job. Efficiency-wise, it's similar to SimGN, okay? So again, it's another example to show that we can do faster and better, okay, by using graph neural network approach to solve some traditional problem. Okay. So now we kind of solve the first problem, which is like given a pair of graphs, right? How we can compute the similarity based on the graph structure, okay? But we still need to address the second operator, which means that we need to represent those graphs as an embedding vector such that we can use some like index to quickly identify the most promising candidates for a query graph, right? So in other words, we really needed to kind of try to learn those operator, which maps a graph into a d-dimensional vector, okay? So that's our goal. And here I wanted to mention that keep in mind that there are indeed different graph neural networks, right? You can really generate a graph level representation, but now we need to think about that, whether they can directly apply to the search problem. So we're going to discuss this later. Okay. So on the other hand, okay, there are also some other approaches that we can represent a graph. For example, the feature engineering based one, right? So, and among them, this graphlet-based feature vector is quite popular. So in other words, we try to identify the small substructure, possible substructure, given the size limit, right? For example, if we consider all the size 3 graphs, right? So then we have like 2 possible ways, right? So we just enumerate all the possible graphlets or the kind of substructure of those small graphs, right? And then once we have this graph, we just try to count how many times I have this graphlet and how many times I have that graphlet. So in this case, then we can have a bag of graphlets representation for any graph, right? So in this way, we can also have a nice representation. But then what's the problem here? The problem here is that try to do the matching itself is NP hard, right? Try to decide how many times this graph contains this graphlet itself doesn't need exponential time if you want to do it in an exact way, right? So that's why really it's not a good idea, okay? So that's why we wanted to propose good representation, graph level representation, right? Such that it's not only its graph level representation, but also it has to be unsupervised. It is general to different downstream tasks, okay? Because we don't know what we're going to use it for, right? And third, it has to be inductive, which means that for a new graph, we have to be able to handle that, right? So then we, in our U-graph embedding paper, right? So then we kind of summarize the existing work, and only our approach and this graph kernel-based one, you can imagine the graphlet-based feature engineering kind of vector representation is one possible graph kernel. So for the details, I'm not going to explain, but you can consider in this way. So only these two methods satisfy all the three conditions, okay? And now let's also think from another aspect, right? So for almost all the existing graph neural networks, when they try to generate a graph level embedding, they utilize node level information. They use node attributes. They use the links within that graph, which actually connects to nodes. That's all, right? What's missing here? What's missing here is the graph-graph interaction information. So it's like why we can have a good representation for a node in a graph. It is because we are able to capture the node-node interaction. So then we can know the relative position of each node. So similarly, if you want to represent a relative position of a graph, we have to introduce this graph-graph level interaction. Okay, so that's the highlight I wanted to deliver here. A good graph level representation should preserve similarity between graphs. Okay, there's no way that we can have a good graph level representation just utilizing this graph level information, okay, which is the main difference of our work to the existing ones. Okay, so for the details, okay, so and also I try to skip the details but deliver the high level idea. The general idea is that in order to capture the graph-graph similarity, right? So we can use, for example, GED, we can use MCS, which do not require additional label, okay? It can be computed just by using the data you have, okay? Then with that kind of information, right, so we can define our loss accordingly. It's very similar to the strategy one that we've mentioned in the SimGN, right? So we wish that the nice representation can directly preserve the similarity that we are interested in, okay? So in this case, right, so then of course you can define your loss function differently. For example, you're saying that, okay, for the final graph level representation, if we directly use this Euclidean distance, then it has to be close to the distance metric that you wanted to leverage here. Or if the similarity measure like MCS or the GED mapped the similarity measure, right? So you say, oh, I just use a dot product of the two graphs, right? So then we can measure the similarity between the two, and we wish that it's close to the ground truth, right? So there's underlying interpretation of what we're doing here. So essentially what we're doing here is like we're going to map each graph into some low dimensional representation. And this representation, if we consider the inner product of the two representation, it kind of determines a kernel between two graphs, okay? So that's something more theoretical in the end, okay? So then we try to compare the embedding of the graphs that we have obtained from our approach and compare it to those baselines, right? So it turns out that if we use some other baselines, which also can get this graph level embedding, but if we look at embedding, right? So we just draw a line here and try to examine visually whether those two graphs are really close to each other. It turns out that it's not the case, right? So if you look at the net MF, right, so it's not the case, right? So for example, this graph is very different from its like nearby nodes. But for our approach, we still draw a line, right? So we can see that actually our representation, so left-hand side is the visualization based on the representation, and right-hand side is just a way try to zoom in and try to output the original graph structure. We can see that these graph structures are indeed very similar to each other if they are close to each other in terms of the representation. So in other words, by using our representation learning, we are able to preserve the manifolds of the graphs. Okay. So also we kind of test this representation on other tests, for example, graph classification. That's better than those baselines. And also we test it on the graph similarity search. It's also very good. Okay, in other words, if you wanted to use embedding to directly conduct a similarity search, it's already very good, right? But still there's a gap between representation, graph level representation to search, as we just discussed, right? So a very easy way to do this is try to build an index for the representation, and then we can use index to facilitate the search. So actually there are lots of different index methodology try to index over the high dimensional vectors. So here I also want to mention something very interesting. So when we say it's low dimensional vector representation, actually is with respect to the size of nodes in the graph. So it's like compared to that, it's a relatively low dimensional, but it's still in practice like 100 dimensions or 200 dimensions, right? So then for index community, they definitely treat this 100, 200 as a high dimensional vector. Okay, so here I want to clarify the implication of this low dimensional and high dimensional vector representation. Okay, so then our solution in that we don't want to make this as a two-stage procedure. Like first try to learn a continuous vector representation and then apply some other index. We want to directly build an index using graph neural network. Okay, so that's why we propose our new methodology called G-hashing. So this G-hashing, essentially the idea that we're going to directly map a graph into a discrete code. In our case, a binary code, which is hash code, okay? So this hash code is going to be learnable, which means that if we change our GED distance into MCS or into other similarity measure, okay, so everything does not have to change. We only need to retrain it, okay? Second, it's going to be super efficient. So compared to the base state of art, we can achieve 20 times speed up because we have this very powerful graph hashing, okay? And third, it's very effective. So although we can make mistakes by kind of missing some promising ones, but for our solution, we do not provide any false, I think I have a typo here. We do not provide any false positive, okay? So then everything is going to be a high F1 score. So because we only provide this approximate solution, okay, so that's why we might make mistakes, but as long as you return it to me, it's going to be a correct answer, okay? So then for the G-hashing idea, okay, so it has this offline stage, which is try to build this hash codes and do the hash index, okay? And we also have this online stage. So this online stage still follows the traditional pruning and verification framework, which means that we're going to use the hash code to prune lots of non-promising graph candidates. And then we're going to use the exact computation to verify whether the graph candidate is really similar to the query or not. Okay. So now let's take a deeper look at the offline stage, right? So for the offline stage, right, so the architecture is also very similar to this SimGN, right? So in the beginning, we're going to use graph neural networks, right, to get the node level representation, and then we use attention to have the graph level representation. And afterwards, we're going to doing this continuous embedding. So then every graph now will be representing very good low dimensional vector, okay? And we're going to put a loss here to make sure that this continuous embedding can preserve the distance measure or similarity measure that we are interested in. Okay. After that, we're going to binarize this continuous embedding using some trick. Okay, for the details, we probably need to read the paper in detail. But we're going to binarize it, and based on the binarized code, right? So we're going to using Hamming distance related loss to measure whether this binary code is with a high quality or not. Okay, so once we using this ground truth to train the graph neural networks, right? So then essentially for any graph in the database, we can have a hash code, which is a binary code, okay? And then we can build this hash index, which means that for each hash code here, we just try to build an inverted index to put all the graphs with the same hash code here, right? And also we're going to also put the continuous embedding after that. So why we want to do that? Because we want to do two-level pruning, which we're going to introduce later. But anyway, for each node, for each graph, right? So it will have a hash code, and also we're going to have a continuous embedding, okay? So then for the online stage, right? So once there's a query, so what we're going to do is like, we're going to first compute its hash code. So this is very quick, right? Because it's just a proportion to number of edges in that graph, okay? Using this graph neural network structure. And then we're going to do this two-level pruning, okay? So we're going to first flip several bits of that hash code for the query. So we can get the candidate hash codes, right? So we use this candidate hash codes to identify candidate graphs using this inverted index, this hash index, right? And then based on that, we can do another level refinement, right? So we can use embedding to compute the similarity between the query graph and the candidate graph. So based on that, we can pruning for the second round for the non-promising graphs. So at this stage, not so many candidate graphs have been left, right? So then we can feed that into the exact solver to make sure that, okay, our final returning result is accurate. Okay, so here is illustration. Suppose it's like a chemical compound graph database. And in the middle, we have this query, right? So it has the hash code as listed here. And we also have continuous embedding as listed here, right? So then for this one, right? So using this hash index, we can kind of quickly identify those several graphs are promising, right? And we're going to use this hash index to prune the non-promising ones, right? And for the remaining ones, we're going to use this embedding to compute whether they are promising or not. We can do second level pruning, okay? And then we're going to do verification, okay? So that's the general idea. And then if we look at efficiency, okay? So our approach, G-hashing, right? So it's like, we have two different variations. So, which is trained over different graphs, okay? So the bottom two lines is the performance, right? Okay? And for the x-axis, okay, so they are just the range query, okay, so which means that we'll do range query 1, 2, 3, 4, 5. Okay, sorry, so this whole thing is a range query, tau equals to 1. Okay, and this 1, 2, 3, 4, 5 is like, can scale our graph database and try to see how the response time change over the size of the database, right? So it turns out that, right, for very large graph database, like 5 million graphs in that graph database, so we can still respond within just a couple of seconds, right? But for the best baseline, okay, so actually there's only one baseline that can handle millions of graphs. But for the best baseline, you can see that it requires 40 seconds to just get the average response time, okay? So that's why our G-hashing technique is very fast. On average, 20 times faster than the only baselines that can work on this scale of a graph database. And for the effectiveness wise, right? So then it turns out that because we can guarantee there's no false positive, right? So which means that the precision wise almost 1. So probably you may wonder why it's not exactly 1, because sometimes if we discard some promising candidates, okay, so then it turns out that the returning result is going to be empty, right? But for the ground truth, it does have some results. So that's why we treat that precision as 0. So that kind of drag down our average precision. Okay. And recall wise, it's definitely, it will decrease when we increase the range query, the tau. Okay. But after we do the F1 score, right? So actually, so we can get the average F1 score for 0.8. So to my personal understanding, right? So when you increase your tau in your range query, right? Actually, it doesn't matter that you miss something, because anyway, there are so many graphs that's going to be similar to the query graph, right? So that's why precision is most important. And in our case, we don't have any problem for the precision side. So that's also something that we want. Okay. So for summary, okay. So here I want to say that graph definitely is a very important data structure that we want to explore, okay. And among them, we can partition the functionalities that we are interested in on graphs into node level and a graph level, okay. So here I want to say that for graph level operations, that's actually more interesting, okay, and especially consider the graph search problem, okay, still a long way to go, but now we kind of provide a first attempt to solve this graph search problem from a machine learning perspective, from this graph neural network perspective. And the current results is very promising, okay. And actually among here, there are many very hard problems, right, at the graph level. So including what we have discussed, the GED, MCS, and including the graph alignment, subgraph matching. Okay, so all those are very difficult problems, but I just fear, right? So if we do it in a right way, and graph neural network should be able to provide a solution which is faster and simpler, okay, and more effective. Okay, and here I also want to mention that there are actually a third type of operator. Due to time, I don't think I should explain it in detail, but I want to illustrate the basic idea here. So the graph matching operator, different from the first two, which we have already done a good job, is like given a pair of graphs, we wanted to train a graph neural network that it can directly output the matched part. So this is very important for the MCS problem, right? So we wanted to directly output what would be the matched common subgraph. So we already have done some progress, and we have released an archive version in this direction, but still I think there's a long way to do that. Okay, so yeah, we spent a long time to study this problem, but so far this is the hardest problem we have met so far. Okay, so I would like to thank all my collaborators. Okay, they are amazing, especially a special thanks to Yunshen, who has done the majority work in this talk. Okay, so probably I still have some time to take 1 or 2 questions. Thank you.
Thanks for this exciting talk. It was really amazing. And the type of results that you presented are really inspiring. So I'll quickly go through the questions. There are a lot of them actually. So the first question is from Al. He asks, can the message passing in the slide with the toy example be weighted by the edges, by the values on the edges for a given attribute? For example, the edge 1, 2 has a time attribute of 1, the edge 1, 3 has a time attribute of 2. So this latter edge would be more intense.
Yes, this is a very good question, and the answer is yes. For the more general graph neural network under the message passing framework, yes, we can append the edge information into the message passing.
Okay, and the next question again by Al is it possible to apply this paradigm to time evolving graphs?
To time rewarding?
Time evolving graphs.
Okay.
Just with time, yeah.
Yeah, yes, we can. So actually we have another work called heterogeneous graph transformer. So in that paper, we have carefully studied how we can include the edge information, the different edge types, different node types, and the time information associated with nodes and associated with edges. Yes, we can.
Okay. So there are 2 more questions on node ordering. So one from Al, which again points out to what defines a good node ordering. And the second is from Lax, who asks how hard it is to find a good node ordering.
Yeah, so that's also a very good question. So right now, what we are doing for node ordering is just like start from the node with highest degree, and then we do the brief search, right? So then how we can measure what is good or not? Actually, it's a chicken and egg problem, because the node ordering, okay, if we solve the problem, then we can kind of solve the matching problem, okay? But we know that the matching problem is a hard problem, right? So it's like, there's no way for us to find the best ordering, because itself is an NP-hard problem. So what we can do is just use some heuristics to find a relative good ordering.
Mm-hmm. Yeah. Okay, so I'll move ahead. Amin asks, what is in the graph terms the intuition behind adding attention mechanism to the similarity search use case?
So is the question to try to understand how the attention mechanism works?
In the context, like what's the applicability of this attention mechanism in the context of the use case?
Okay, so
and what does attention mean when you talk about attention in terms of the graph?
Okay, so here the attention is like, because we want to move from the node level representation to the graph level representation. So that's why we want to aggregate all those node level representations together, right? So different than we need to understand which node is more important. So it's going to be weighted average. So we wanted to put those attention weights, so then we can get a weighted average. So we essentially try to understand in terms of the graph similarity comparison or computation, which node should play a more important role. So then when we generate this graph level representation, we're going to put more weights on top of that node.
Yeah, that makes sense.
Okay.
Next question is from Amarnath Gupta, who asks, how can these methods be generalized to graphs with node and edge properties?
Yeah, so here for graph neural network, right? So essentially it can handle the node properties, right? So because in the first stage, it will transform the raw feature of each node to do the aggregation and do transformation, so it has no problem. And for the edge property, it relates to the first question. So we can append the edge property, such as time or edge label, okay, into this message passing framework.
Yeah. So the next question is from Xuan Lei, who asked, in slide 39, are all graphs represented in a single vector space? If so, are we assuming that these graphs share certain similarities, or they can be completely different?
My screen's stuck here, so yes. So because they have to be comparable to each other, right? So that's why they have to be in the same space. Otherwise, they're not comparable.
Mm-hmm. Mm-hmm. And yeah, the second part of this question was, are we assuming that these graphs share certain similarities, or can they be completely different?
Yeah, I think that this question related to something else we are studying, which is called pre-training. So our thinking side is like, when we do this, right? When we train something on a set of graphs, do we need to assume those graphs like come from the same domain, okay? Or if we train something on the graph, let's say it's chemical compound, can we apply the neural network that we have learned to another domain, let's say like software, right? So for this part, I just want to say that for the preliminary answer that yes, to some extent, the knowledge can be transferable. But we also observe that if the graphs for training and the test, they're coming from the same domain, then the performance is definitely better. So indeed, they have to share some similarity if you want to have a good test results.
Okay. Yeah. So the next two questions are a bit on the implementation and the measuring, like how the performance is being measured in terms of the efficiency. So Julian asks, what language or framework do you use to implement these algorithms, and what computing platform is the running times obtained from?
Okay, so for implementation, what implement is like PyTorch, because it supports like the dynamic computational graph. And all the code actually you can find either on my personal web page or Yunsheng's web page. And for the comparison, I want to say that it's kind of unfair because most of the traditional approach they are implementing using C++ or C or those much more efficient language. But even so it's like we don't have that advantage. Okay, but even so, our algorithm runs faster, and also we not only compare with them in terms of running time, which I know that it's kind of not fair, right? But if we directly compare with the time complexity, we can see that our approach indeed has this kind of advantage in terms of efficiency.
Okay, and the next question in this part was, are you using DBMS solutions to implement these algorithms?
I think it depends, right? So for example, for the pruning and the verification, kind of this idea actually is borrowed from database community. Yeah. But for the other things, right, so it's also, it's come from different communities from machine learning. So I think this works kind of combination of both communities. Yeah.
Okay. And one last question, which will be from my end. So how well do these algorithms scale in terms of the training time? So I am assuming these query times that you have shown in the experiments are the inference times, but how long does it take to train such very sophisticated neural networks on such large tasks?
Yeah, it's a very good question. Yes, so we have to train it for quite a long time, sometimes up to a couple of days. Yes.
And can these scale to million scale networks, or are we still a bit far from doing, training on such large networks using graph neural networks?
Yes, we can. So for graph neural networks, right? So for today's talk, actually focus on the small graphs, but like we have graph database with millions of graphs, so we can handle that. And another setting is like we have one huge network, like social network with maybe millions, even billions network. So we can also handle that, but we need this very smart sampling technique.
Mm-hmm.
Yeah.
Okay. That's okay. So I don't think there are any other questions. So I would say let's thank the speaker for such an engaging and exciting talk. Yeah.
Thank you.